Welcome to Programming in Modern C++. We are in week 11 and we are going to discuss module 53 now. In the last module, we started discussing about unnamed function objects in C++ called lambdas or closure objects. We understood the difference between lambda expression and closure object and its detailed structure, discussed about its issues about its parameter and what is meant by capture of lambdas. Now, we will continue in this module with learning different techniques for writing and using lambda expressions in C++. Specifically, we will understand a wrapper, polymorphic wrapper called std::: function from the standard library of C++ and understand generic lambda support in C++ 14. We will also learn how to implement recursive lambda expressions. Whatever we have seen so far are non-recursive in nature. How to do that in C++ 11 and in C++ 14, and we will be exposed to several practice problems which will be left in this presentation for you to practice at home. Here is the outline and will be available on your left panel, as you know. Now, before we start, let me just give a quick recap on what we have learnt in terms of lambda in C++. This is what was done in the module 53. So, a lambda expression is an unnamed function, as we have learnt, for specifying lightweight functions, and for this the compiler generates a functor like class for which at the runtime an instantiation is created for a functor function object called the closure object. The lambda expression can have 0 or more value parameters or reference parameters in it that are used in its body. Free variables that are not parameters are captured by value or reference. This is what we have learned. So, just to recap, here is a simple example of a lambda expression with one parameter v, and it is trying to do this computation where it takes the residue of v divided by m underscore, where m is a free variable in this lambda, and keeps on accumulating that, as you can see here. So, for this m and count, where you capture, both are non-parameter variables. So, they are free and they will have to be captured. We capture m by the default all by value. So, m will be captured by value, so that at the beginning, at the time of instantiation, the value of m will be value of m underscore will be copied and stored inside the lambda object, whereas a reference will be created for this count variable. So, this is a capture by reference because we want to make changes to it, and that changes should be reflected outside of this lambda, right. So, this is the basic lambda expression that we have learnt, and using this lambda expression, which is passed on to a for each algorithm to apply over the values, the iterator values of a vector. So, we first add 3 values to the vector by doing put, right, one after the others. We have a vector of values 3, 7, 8, and then using m underscore as 4, we compute the lambda g dot extra. So, it will compute 3% 4, 7% 4, 8% 4 and accumulate that, and if you run, you will see that you are getting a value 6, right. So, this is what we learnt about the lambda in the last module, right. So, before we proceed further, let me introduce you to a library function, a wrapper function in C++ standard library called as std : function. The purpose or use of it will soon be evident in terms of expressing lambdas in a more powerful way, right. So, std : function is defined in the functional component of the standard library. So, it is like a template which is kind of it is a variadic template, which is again something that we will learn about later. Do not worry about all that. All that it is trying to say that its basic declarative syntax is like this. So, in std : function, as a lambda parameter, you pass all of these, where R is the type of the return from a function. So, it is kind of it is a polymorphic wrapper for function objects. So, what do I need to say for the function object? What is the type of its return value and what are the types of its parameters? So, types of its parameters are A1, A2, A3 and dot 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 means that there could be as many parameters as you want, and there may not be a parameter also. It depends on all of that. So, using this std : function, you can define the type for a normal function pointer, a member function pointer or a function object, including the lambda closure object. So, these here are some examples of if it is a function pointer, if it is a functor or if it is a member function. Now, what you see interestingly is in each one of these we are taking a function, a computation which takes two integers and return an integer. But the way we write it, the syntax and the details of how we write a function pointer or how we write a functor object or how we write a member function pointer, all of those vary widely. Whereas, using std : function, we can define their type in a very uniform, identical syntax and semantics together, right. So, that is why this is called a polymorphic wrapper. Polymorphic because it is amenable to all different kinds of forms, and it is a wrapper because it actually does no computation, but it just helps you tell what is the type of the function. And the function object that you define could be without any callable objects also, without any of these. It may not have any of these. If that happens, then we say it is an empty function, and calling an empty function certainly will give you an exception. So, this is the empty function. Let us look at examples of std : function, right. So, if you see what I have done here, I have defined a simple function here. I have defined a function object here, you can see struct. So, this is a function object, and I have defined another function object where there is a value, there is a data member, that is there is also a state. So, a function object without any state, a function object with a state are the three types that I have defined. Now, you must focus on these definitions, that is where we are declaring different functions. So, just first note that all of their types are the same in terms of the std : function, because each one of them takes an integer and returns an integer here, here and in here. All of them actually take an integer because value is an integer. So, you write it as simply as this is the return type written first, because you will have only one return type, and within the parenthesis we have int to say there is one parameter and that is of type int. So that is same for all these functions, and therefore all of their wrapper types are same. And with that we define 5 different function variables f1 through fn. One is by just directly taking the function, one is taking the address of the function, one is taking the functor object, one is writing a lambda expression which is equivalent to a functor object, and one is basically using a standard function object from the standard library std::negate, which given an integer basically gives the negative of it, minus of that. And with that we use these functions exactly in the same way we use the function. So it's like we can declare a function with its type like we can do for any other variable. In a function notation, you have to, if you have to do it, then you would have required to write it as what is the type of this function. Then either you write it in terms of a forward declaration and you say half int, so just write the prototype, or you have to write it as a function pointer notation. But here you are being able to write it simply as you declare a variable, right. So this elevates the functions to the first class objects that we have been talking about. And then once you have defined that, then they are function objects. So irrespective of whether it's a simple function or a pure function object, or with state, without state, or it is a lambda, you can invoke them in the uniform syntax. So this uniformity is what is given by the std::: function, which is very, very important for generic programming, because we want to write everything generically here. In addition to this, uses these two functions and functors. For the function with the state, we can actually just see how we define the type. We are defining the type as the return type is int, as you can see, and the type of the parameter I am specifying here is a reference to this functor object. So once we do that, then this functor object as a whole is the type that we have, and therefore the members of that, there are two members. One is value, which is a int variable, and the other is actually a function fifth. Each one of them can be actually represented again by the same wrapper type, and I can say value is my value : value, the function is my value : fifth, and so on, and I can use them exactly in the same way, right. So this uniformity is what is important, provided by the std::: function wrapper. Here I have given an example. This is for your practice. This is an example of a pipeline operation, that as if you have a value and that passes through number of function calls, and so here you can see that how these functions can be put uniformly in terms of std::: function, a vector of std::: function vector. So this is where you should focus on, that you can make a vector of such functions and keep on applying them one after the other, getting the effect of a pipeline. Read this example carefully and try to run it, and you will get a complete hold on that. Now let me come to the meat of what I want to discuss, that is about generic lambda in C++14. In C++11 you have seen the lambdas, right. In C++14 this has been somewhat enhanced. How enhanced? In C++11 I could write a lambda like this, which takes two integer parameters and adds them and returns the added value with the return type int. I can write another lambda for two doubles. Now this brings us to the same question of, functions having similar functionality, but because of their argument types they need to be, or return type, they need to be separately declared. So how do you work around this problem? We know that we can use template. So in C++11 you can write this as a template. You can say that it is of type T, where T is a template variable and returns a type T. This is what you can do in C++11. In C++14 you can do something interesting. What you can simply do, you can just say auto A, auto B, and then write this expression. So what it does, depending on the instantiation, the compiler deduces the type of A and B, and from the type of the expression A plus B, it deduces the return type. So the compiler does all that job, and you can write very simple expressions. So an example will help you understand this. Here are three different functions for adding integer, for adding double, and for adding string, which is basically concatenation. If you want to unify, then you can unify them in terms of a template, as I just mentioned. In C++11 you can just make it simply by using auto. So if you use the first three in C++11, then every lambda has a different name. If you use the template version in C++11, then the lambdas have the same name, one name, but you need to specify the template type, whether it is int or it is double or it is string, right? Only then the compiler can do the proper conversion and do it. But in C++14, where you have just declared as auto, you don't need to do anything. You can just write them as simply as instantiation, and from the parameter the lambda deduces, the compiler deduces what is the type of this auto A and auto B, and accordingly what is the type of the return value. Please note that for string you need to convert the constant C strings into a string object before calling this this version of the lambda, because otherwise if you just pass them like this, here in this case you did not have this problem because you are using a separate function which knows that they are string. Here you did not have a problem because again the template parameter is told to be string. Here if you do not say string, if you just pass within double quotes good and within double quotes day, then the type that it deduces is const_cat star, right? Naturally const_cat star cannot be added. So here this difference is you will have to specifically say what type your parameters are in the call, right? So this is the only difference that you have. Now in terms of return, it can deduce the return type automatically based on the type of the return statement, or you can specify the return type by a suffix return notation of saying decl type. You can say decl type A plus B, you can, which will be same as this. You can say decl type A, that is I always want the return to be of the first parameter type, or decl type B. It all depends on what you want to do, and based on that here you will be able to see that when you have operations with mixed parameter types, how this is going to behave. So this is a very powerful feature, and it can be used more generically, like here is a sorting example where I have defined a comparison. I have defined a comparison lambda using auto A and auto B. Return type is bool, and this comparison operator has to be available for the types deduced for A and B. And in this example I have three vectors, one of integers, one of double, and one of string, and using the sort algorithm from the algorithm component of the standard library, I can sort them with a great ease. So, you can see how small this code is, and here you can see that I have used a print element global function where I have used range for kind of construct to easily print them in one line, right. So, this is how auto in generic lambda in C++ can greatly ease your efforts. And also the generic lambda, if there is no capture like in here, if there is no capture, then any lambda can be also assigned to a function pointer. So, here is a function pointer and here is a lambda, and I am just putting it in the function pointer. And if I have appropriate function pointers, one is from int to it, another is into void, another is from double to void, then I can use assign the same lambda to them, because the appropriate parameter type will get deduced by this auto x in the generic lambda, right. So, generic lambda is a really powerful tool that you have in terms of C++ 14. Now, equipped with all that, let us look at how do we compute recursive functions. In computer science, in all through, computing recursive functions is the most important. So, to understand this, I am using an example recursive function, and for a change I am not using Fibonacci or factorial. You must be tired of them, you will get them as your practice exercise. Here I am using a function count n, count once, given a decimal number n, which will count the number of ones in the binary representation of n. So, if say n is 5, its binary representation is 101. So, there are 2 ones in the binary representation, right, 2 ones. So, therefore, count 5 should be 2. Similarly, if it is 14, then there is 3 ones in the binary representation. So, count 14 should be 3. So, how do we recursively define it? Very simple, that I will see what is the whether the least significant bit of a number is 1 or 0. If it is 0, then the number of ones in this number is same as the number of ones in the remaining set. If it is 0, then the number of ones is same as the number with removing the least significant bit, which is n by 2. So, this is the condition. If n is even, the LSB is 0 and the count is same as n by 2. If it is odd, as in here, this is LSB is 1. So, the number of ones in the entire number is the number of ones in n minus 1 by 2, 5 minus 1, 4 by 2, that is 2, plus 1, this particular one. So, it is, if n is odd, then you have this, and the exit condition is number of ones in the representation of 0 is 0. So, with that we have this recursive definition, and we can easily write it as a pure simple recursive function. If n is 0, then it is 0, otherwise it is count n by 2 plus n percentage 2. These two get merged together, because if n is odd, then this is 1, if n is even, then this is 0. So, I can make use of that and write this, and I can have a, here I have defined a print lambda to print the values for different values of n, right. So, this is a recursive function. So, what I want to do is to write it as a recursive lambda, write it as a lambda. So, if I write down this expression, the similar expression with the lambdas, and say auto this, because it is recursive, then I will get a compilation error. I will get a compilation error. Why? I will get a compilation error because I am trying to deduce the type of count ones for here, but that deduction has not completed yet. So, it goes in the circle, and therefore, this is the compiler will not be able to do this. So, how do I take care of it? I have to tell the compiler that count once is a function or a function object, so to say, which takes an integer and gives me an integer. I have to first define that symbol, and then I will be able to define the rest of the lambda, right. So, instead of doing auto, I actually define the prototype of the function, which is I do by the std : function. Now, we can see why we studied about std : function. With that, this becomes a defined symbol, and therefore, I can make use of it in the lambda. Now, why the parameter is n, which is clear. This expression is clear. Return type will have to be int, but if you write this lambda, then count once is a free variable in the lambda. Therefore, you will have to capture that by reference, and whatever results is what you say is the definition for count once, right. So, now you do not have a problem, because you have been able to define the symbol count once ahead of defining the lambda. So, with that, using the earlier print lambda, I can write the same thing. So, now you can see how you can write recursive functions in C++11 using lambdas, right. So, in the remaining few slides, which I am not going to discuss, I have given a number of practice examples. This is an example of a co-recursive lambda between F1 and F2. F1 actually calls F2 and F2 calls F1, and you will have to see how to. And the common thing is all of them use the std : function pre-declaration for the functor variables. Then there is a solution for factorial. You should not see these solutions, you should try to write them first, and if you cannot, only then you see the solution and try them out. There is for Fibonacci, and there is so these are the practice examples that you do. Now, in C++14, I can write, I have generic lambdas. So, I can write generic recursive lambda in C++14. That will get rid of the std : function requirement. So, what I do a simple trick. The trick that I do is, the problem was that earlier that this symbol was not known to the lambda. So, what I will do is, I will make this symbol a parameter of the lambda function itself, lambda expression itself. I cannot do that in C++11, because without std : function, I cannot say what is the type of this symbol count once, but here I have auto. So, I say it is an auto, and it will give me a value, temporary value. So, I say that it is a auto, which is a R value reference. So, count once is a symbol. So, this count once lambda now has two parameters. One is count once as a R value reference and count 10. So, you call count once in a little bit funny way. This in count once, the first thing you pass is the parameter lambda, and then the whatever is the numeric parameter. But with that, and using the same old print lambda, you can implement the same thing without using std : function. If you are really irritated about passing the function as the first parameter to the function, then you can always write a wrapper. This is an example to compute power of a number. So, base to the power exponent is what we are trying to do, and is a recursive definition for that, which you can read and get convinced that it works, but it is trying to pass the function itself as a first parameter. So, it will require that when I invoke power, I will have to say power, and then base exponent. So, this should be the actual call. So, what I do, I write another lambda pow, let us say a different name, where I pass two parameters, base and exponent, but I capture power by value, and by therefore, I will be able to write pow only for base and expression, right. So, this simple wrapper will give me a very nice looking recursive lambda for doing any recursive computation, right. So, that is That is all that I wanted to show. There is another example for factorial again, which you should try out yourself. Writing it with std : function you have done. Now try it without std : function using the generic recursive lambda in C++14. Similarly for Fibonacci, you should practice both of them and other functions that you want. The last that I want to mention to you is what is known as generalized lambda capture in C++14, right. So, in C++11, if you did a capture, then in the capture you can just capture on the symbol either by value or by variable, right. But C++14 gives you a way to capture in a more generalized form. Particularly what I can say that capture u by move u. So, treat move u as u. So, what am I doing? U is a symbol. So, per se whatever u is defined here, you will see unique pointer later on. Do not worry about that semantics part right now, but all that you know is u is defined as a symbol. So, u is a L value reference. I want to actually pass an R value reference. So, I do move. This is std : move from the library, right, and call that u. So, this is what I could not do in C++11, and here I can do that. So, it basically does not give a copy of, it does not, it is a pass by, captured by value, but it does not take a copy of it, but it just moves whatever is available in u. You can rename in the process also. You can give the operated capture a different name, and you can do other things like you can also have a new local variable in there. There is no local concept of local variable so far in the lambda, right. In C++11 you have parameters and you have captured variables, but here you can have local variables. So, x is outside the context and I am trying to define this lambda. I say lambda ampersand r is equal to x. R is not defined before this. So, r becomes a reference to x and I can do operations with r. So, r is a local variable. Similarly, I say y is x plus 1. So, this is captured by reference, this is captured by value, but they are local variables, local symbols available only within the lambda, and according to that I can add 2 to r, which will actually mean that I am adding 2 to x. So, x will become 6 and I can return y plus 1. Here y was captured by value. So, the value of y was x plus 1, as you know, captured by value, the value will be copied at the time of instantiation. So, that was set to 5 and then 5 plus 2, 7 is what is returned. So, this is the generalized lambda capture in C++14. So, there are more features, some more features that have come in C++17 and C++20 in terms of the lambdas, but we are not getting into those details. Once you get comfortable with using lambda, you can easily look up those, though they are not major enhancement, but they are just somewhat making things somewhat more powerful. So, we have learnt about different techniques with or without using std : function to write non-recursive as well as recursive lambda expressions in C++11 and 14, but most importantly several practice examples have been given. So, please try them out and test those thoroughly. Thank you very much for your attention. See you in the next module.